All right, let's get started, everyone. So good afternoon and happy Halloween. It's my great pleasure today to introduce Chris Laumann from Boston University. Chris is a professor of physics at BU. He got his PhD from Princeton working with Shivaji Sondhi and was a Lawrence Golub and ITAMP postdoctoral fellow at Harvard prior to moving to start his faculty career at the University of Washington, where he was for several years prior to moving to BU. Chris is one of the most eclectic physicists of his generation with broad research interests in condensed matter physics and quantum information. He has contributed significantly to the theory of strongly correlated electron systems, topological physics, many-body localization, spin glasses, quantum optimization, and is also a key contributor to various experimental efforts in both solid-state and synthetic platforms. Chris is also giving tomorrow's Q-Farm seminar, where he'll talk about something very different, where he'll be talking about efficient routes to state tomography. But today, it's my great pleasure to introduce him to hear about his exciting recent work on quantum spin ice.
All right. Thank you. Can you guys hear me? I hear myself. So I assume you can hear me. Well, thank you very much for having me. I want to tell you a story about quantum spin ice. I apologize, I'm going to get confused. One of these is a laser pointer, and one of these will actually advance the slides, and I'm sure I'm going to get it reversed regularly. So, okay. Right. So this is a topic which I started working on maybe 4 or 5 years ago, mostly because I think the story that I'm about to tell you is so pretty. Okay, so hopefully I will convey that. If I manage to convey that the story of quantum spin ice is pretty, then my colloquium will have succeeded and I will go home happy. Okay, what is this about? Well, I have to unpack it a bit. There's, oh God, clicker. Yeah, this is going to be very bad. Let me say up front, and this talk is based on a set of works here. Some play a larger role than others, with various collaborators that I'll come back to at the end. So, what are we talking about? Well, to get started with quantum spin ice, we should actually start with something which we're all much more familiar with, which is water. Does everybody know what the most important feature of water molecules, H2O, is?
It expands when it solidifies.
Wow, so fancy. Even simpler. They're shaped like bananas. Okay? That feature, that it's bent, is related to the fact that it expands when it solidifies. That it is a bent molecule, a small bent molecule, is the most important feature of water. This means that water, the water molecule, I'll also point out it's bent at about 105 degrees. The water molecule, accordingly, is polar. So one end of it is positive, the other end of it is negative. The hydrogens are more positive, the oxygen is more negative. And that's very important because it's a very light molecule. If it weren't polar and didn't have this structure, it would not be liquid on Earth, right? Most light molecules are gases at standard temperature and pressure. But these ones bond much more strongly to each other because the positive guys can get close to the negative guys and form hydrogen bonds, which make them like to hang out close to each other, right? So this is actually really the most important feature. Of course, it's not always liquid and wet on Earth. It can become ice. I thought this was a really cool photo. I was hoping to find a photo of some body of water near Stanford that freezes, but I couldn't. I spent some time, but so below 0 Celsius, 273 Kelvin, water freezes into ice, which is a very peculiar solid because the water molecules are bent. So it looks something like this. There are oxygens, water molecules. Now I should have a laser pointer again. Over here, the oxygens form a regular full forward coordinated lattice, while the hydrogens form hydrogen bonds between them. And the fourfold coordination is quite natural because that 105 degrees is very close to the angle in a tetrahedron. It's not exact, but it's very close. So the thing is that in water ice, actually the reason it expands when it freezes is because this is a very open structure. I mean, you can kind of see there's a lot of space in there because they wanted to form these tetrahedral angles. But actually, just putting the oxygens on that regular lattice does not freeze where the hydrogens need to sit. Okay? So that's the next important feature of water ice, is that actually I can order the oxygens, the basic geometry, and the hydrogen bonds still have a lot of choices. The hydrogens have a lot of choices, and this was first pointed out by Bernal and Fowler in 1933, who said that perhaps some peculiar properties of the thermodynamics of ice could be understood because they just needed to satisfy a 2-in, 2-out rule. What does that mean? Well, if I look at this central water molecule, I see that 2 of the hydrogens are close to it, so I can say they're in, that's covalently bonded, and 2 of them are far, that's the polar bond, right? And 2 years later, Linus Pauling pointed out that that means there's actually lots of choices left over, even in this crystalline ground state. Let's see. I'm going to try to show them to you. If you look here, I just moved around some hydrogens and found another state where the oxygens were in the same place. Okay? There's another one. So there's a lot of choices consistent with the ordering of crystalline ice. And we can actually count it. This is more or less the counting that Pauling came up with as follows. There are 4 choose 2 is 6 orientations for each of those water molecules. I have to pick which 2 of the 4 bonds have the hydrogen close. And if I did that independently, then there'd be roughly a half chance that each of the neighboring water molecules would agree that the hydrogen bond was correctly created. Okay? And from that estimate, we get that there are 6 to the number of molecules times a half to the number of bonds, which is 2n, configurations. And so Pauling says we take a log of that and we get that the residual entropy of ice is n log 3/2. Okay. Okay, which is pretty big. And actually, I didn't include any slides about it, but was measured to within a couple percent. It's actually surprising. This is a very good estimate. It neglects a lot of correlations, but it's actually a very good estimate. It was measured to within a couple percent a couple years later by calorimetry experiments. Okay. Okay, so this should really upset everybody in the room. Oh, it's kind of a dead room. Is everybody really upset? Really upset, right? Why should you be upset? Because it violates a law we all hold dear, which is the 3rd law, which, by the way, is the one that didn't make it into the AP curriculum in this country. The 1st and 2nd law did, and the 3rd law just did not make the cut. So nobody who came in taking AP physics knows what it is. Okay? But the 3rd law of thermodynamics is that the entropy goes to 0 as temperature goes to absolute 0. Okay? So if I keep cooling this ice off, something's got to happen. Okay? Now, in water ice, what happens is that below around 70 Kelvin, the ice undergoes a structural phase transition, which is actually ferroelectric. All of those water molecules line up, and you get a net polarization. That's called ice 11, which, by the way, was only discovered in the 70s. Because it's really hard to get water to actually freeze into that state. The other one is very metastable. Okay? But anyway, so ice completely orders below 70 Kelvin, once it's sort of done this, all that entropy is gone, so it freezes out. Actually, ice is really complicated. This is the phase diagram, which I snagged from Wikipedia. I think it's a very nice, colorful image. Here's, where we live. That's liquid water. This is our coffee. And then we come down and it freezes. And these 1H and 1C are whether it's hexagonal or cubic. It's basically very similar looking. And then there's this ice 11. And if you go to high pressure, actually these very high pressures up here, like this phase diagram up here keeps getting extended and refined, right now. There's still people finding new exotic phases of ice. Okay, so good, that's ice. We want something more exotic to happen as we go to low temperature. Okay, so we want something else than just freezing. That's the boring answer when you do quantum condensed matter. Can we come up with some analog, some other system which is ice-like? Okay, and all we need is something that can point in or out, to have this 2 in, 2 out rule. Okay, so how do we do it? Well, let's stick an arrow or a spin, an easy access spin, on the midpoints of that crystal that we were just looking at, the ice crystal. Okay? And that lattice actually is a system of corner-sharing tetrahedra, because the midpoint lattice of that ice lattice makes a bunch of tetrahedra. Okay? And now I put spins on them. And this lattice has a name. It's the pyrochlore lattice, which tells you absolutely nothing about the fact that it's corner-sharing tetrahedra. It just is because there is a class of minerals, which were presumably found next to volcanoes, which are called pyrochlores. Okay? They look like that. And actually, so the picture on the left there is a picture of that mineral, and the picture on the right is terbium titanate as grown by the Mundi group by MBE. So that terbium titanate is a member of this pyrochlore family of materials. Okay? There's also a number of, at least proposals, to make synthetic ice or synthetic spin ices in Rydberg arrays or other kinds of engineered quantum systems. Okay? But for this talk, there's actually a lot of 2D analogs of spin ice and quantum spin ice. I want to talk about 3D. It's quite different. And so as there are proposals about doing this in 3D, but there are no 3D experiments of that synthetic type, so let's table it. Okay? Okay, so let's come back to these materials. These are what they are. They're rare earth pyrochlore magnets. They generically have this formula, A2B2O7, where the A's are magnetic rare earth ions. They come from these blue guys in the periodic table. The B's are typically non-magnetic kind of spectators. And actually, the pyrochlore lattice is a little bit more complicated than corner-sharing tetrahedra. It turns out it's 2 lattices of corner-sharing tetrahedra that interpenetrate in this way. But for the magnetic properties, typically you ignore the red one and just think of the blue one. Okay? There's also a lot of oxygens, which would just be confusing to look at, so they're not there. Okay? Great. So what are the materials? There are 2 materials that are called the classical spin ices. They are holmium and dysprosium titanate. They're kind of well established experimentally. They're very well studied. A lot of their, there's actually a lot of interesting physics in their intermediate temperature regime where the ice rule is active. But again, actually, if you go to very low temperature, they order. They order in various kinds of antiferromagnetic orders at low temperature, just like ice 11 does for water ice. Then there's a bunch of what are known as candidate quantum spin ice materials. I've listed a bunch of them here: ytterbium titanate, praseodymium stanate, praseodymium hafnate. There's a lot of them. They go in and out of fashion of how candidate they are or whether they're doing something else at very low temperature. There's reasons for that, which hopefully will become clearer as we go. But let me just say for here, you know, for the rest of my talk, I'm not going to care so much about particular materials, but there are lots of them, and it's sort of active to hopefully see some of the things I'm going to tell you about next. Okay? Okay, so let's come back to, you know, I've alluded to it multiple times, this quantum part of the spin ice story. So here is my lattice of corner-sharing tetrahedra. The starting point for understanding it is that we have two-level easy access spins on each of these atomic sites here. And the sort of classical spin ice Hamiltonian is very simple. It is just that I have a sum over nearest neighbors, that is all these bonds on these tetrahedra, of SZSC. It's an Ising model. Okay? Now, the thing I will caution you is that the Z here is a local Z, of which there are 4. But it's a convention to call that Z. You have to do a little bookkeeping to keep track of it. It's not a big deal. Now, here comes, I don't know if it's the hardest part, but the biggest algebraic step in the talk. Okay? There is a sum over all these bonds. These 4 guys on this tetrahedron are all coupled to each other, which means I can rewrite this sum as a sum over tetrahedra, sum over the spins on the tetrahedra squared. Okay? All to all coupled means I can square the sum up to a constant. Great. That actually is fantastic, because now I can look at it and I can find the ground states. It's a sum of positive things, assuming J is positive. By the way, does that mean that J is ferromagnetic or antiferromagnetic? Very curious, right? Well, it kind of looks like antiferromagnetic. It's positive, it's making these spins want to sort of add up to 0, but I picked an SZ that was at an angle, right? And the angles are bigger than 90 degrees. This is actually a ferromagnetic coupling in physical units. Okay? Anyway, just a piece of trivia for you guys to have at the next pub quiz on spin ice. Okay, so because I now have this sum of just basically plus or minus 1s, and then I square it, it's easy to find the ground states. It's these ones we already met. 2 pluses and 2 minuses adds up to 0. Right? Okay. So ground states is 2 and 2 out, and then I wrote divergence free. Well, what does that mean? Well, I can think of the total spin, SZ sum, this thing, as being how much the spin is pointing out. It is literally a lattice divergence of this spin field. Okay? Okay. So now let's ask about excitations. They're called spinons. They're defects in this ice rule, so let me show you one. There it is. I flipped a spin. And when I flip a spin, now this tetrahedron has 3 in and 1 out. That one has 3 out and 1 in. So I can define something I'll call the spinon charge, which is just the divergence. It's negative here, it's positive there. Source and sink. Okay? Neat. If I flip the next spin there, notice I healed the defect, and I moved the spin over, but I didn't change the energy, because my energy only depended on the fact that there were defects. Okay? So the flip fractionalizes into a spinon-anti-spinon pair that can separate at no energy cost. This is classical fractionalization. It underlies what I said was kind of the interesting physics in classical spin ice. We're going to dress it up a little bit more in a minute. I don't know. It's very simple. There's actually more that you can say about it. It turns out that even in this classical system, these spinons can separate energetically, but there's an entropy cost, which turns out to be Coulomb for them to separate. Okay, now we want to go quantum though. We don't want to talk about entropy. So what do we need to do? Well, let's think about this Hamiltonian. So here's my dominant term. It's this classical ice Hamiltonian, which leads to this huge ground state manifold, which is entropically large, lots of states, all the 2 in, 2 out states, which satisfy this divergence-free condition. And if I flip a spin, I create a spin-on anti-spin-on pair. I got to pay for it. And then I can move them around. So there's lots of states up here as well, right? If I add anything that is off diagonal, it's going to start causing quantum fluctuations in this picture, right? And one thing you see is that anything which is off diagonal is going to flip spins. This one flips 2 spins. And if I flip 2 spins, I'm going to create spin-ons and anti-spin-ons. I'm going to raise the energy, okay? So, on the other hand, I can't violate this Gauss law at low energy, because all the low energy states, which are separated by this gap, satisfy it, right? So the leading thing that can happen as an effective Hamiltonian projected into this ground state manifold here turns out to be this ring exchange term. Now, why is that? Pretty simple geometry. The shortest loop, I guess I don't have a picture of it. That's a mistake. I should have had one. The shortest loop on this lattice has length 6. It looks like a slightly crumpled hexagon, actually. And I can't, if I start in an ice state and I flip a spin, I definitely create defects. And the only way I can get to another state which doesn't have defects in it is to flip a closed loop of spins. And then there are going to be no endpoints where those defects are attached, right? And the shortest loop is this. So whatever I stick up there, I'm going to end up generating this ring exchange Hamiltonian at low energy. Okay. Now, before I go to the next slide, what should I expect to get? So I have to have an effective theory. Now I want to give you a coarse-grained picture of what happens. And you have an effective theory where there is some field which is kind of vector-like because I can take a divergence of it, and the divergence is forcibly 0. It satisfies Gauss' law, but I'm creating fluctuations in it which are kind of curl-like, right? Because these are putting in and out this SZ in coherent rings, right? So what does it sound like? Oh man. Okay, fine. Come on, guys. I got nothing. We need energy here, a little energy. It's Halloween. So it gives me an emergent Maxwell theory, okay? Why? Because what are photons? They're transverse fluctuations of a vector field, the electric field. Why are they They don't create divergence because they have to satisfy Gauss' law with no charge, right? I'm obviously skipping some steps in writing this. You can, if you want to, be more formal and sort of derive a lattice version of this Maxwell theory and then say, well, it can, it's a compact U1 lattice gauge theory, which turns out to be in the deconfined phase. At the end of the day, really, this is kind of the best motivation. I have a vector field which is divergence-free and is fluctuating within that constraint. This is what it can do, okay? It could confine, but we have verified, or by we, I mean these guys, and then me in some later calculations has also seen it, that in fact the ice model is in the deconfined phase for large ranges of parameters, okay? And so this is the effective description. And what do we have? We have what people call an emergent quantum electrodynamics. There is a very low energy photon. I've labeled it by little a because this is one of the horrible parts about doing ice physics, spin ice physics, is that it's an emergent quantum electrodynamics and everybody wants to name the fields in it E, B, and A. But of course, there are, honest to God, E, B, and A fields in our universe, right? And it's really horribly confusing to remember which one you're talking about. And then you write papers, and there's different conventions about which ones you call the emergent E and the emergent B, and some people swap it, and this is just a total mess, okay? So I'm going to be extremely pedantic looking and tell you that this excitation, which is a linearly dispersing, transversely polarized vector-like mode, is a little a photon, and little means it's the emergent field. It's actually some kind of spin wave. It's a transverse kind of ring exchange like spin wave, okay? This up here, the thing which is charged and coupled to this photon is the spinon. It was the excitation in the classical spin ice because it's the thing that actually sources the electric field, okay? It has a big gap. That was the biggest energy scale in our model. And then, because this was a compact U1 theory, there's actually gapped little b magnetic monopoles, okay? Which are configurations of this effective theory where there's a magnetic field pointing outward. It has a source, okay? So those are kind of the quasi-particles in the theory in this emergent electrodynamics. Okay, great. Everybody's on the same page, or they're asleep. Now, what is the plan for the rest of the talk? So hopefully I've sort of illustrated how you get from ice to emergent QED and spin ice. Then I'm going to tell you a little bit about about the fine structure constant, or the coupling in this effective theory. And then we'll talk about how we could imagine probing some of the effects of interactions in the theory in neutron scattering. And at the very end, I'll tell you a little bit about some of our recent predictions for other kinds of ways you could look for this state. Okay? Good. So I already said a few of these things. Let me just reiterate. You know, this is emergent QED. It's not your ordinary electromagnetism, though this looks a lot like the Maxwell-Lagrangian. There's a few differences. It's actually not Lorentz invariant as soon as I, remember how the charge energetics work. So the effective theory for the photon is linearly dispersing. We could call it Lorentz invariant if we want, but nothing else actually has to have that symmetry. The charge and the anti-charge, these guys, they're bosons. They're not electrons, fermions, okay? It contains magnetic monopoles. I don't know, is anybody here searching for cosmic magnetic monopoles? Any searches at Stanford? No? I don't know. Yeah, that's what I thought. But it's still the case that people love searching for things that aren't there, right? It's like an important part of physics, right? So anyway, as far as we know, they're not there, but they are in this system. The speed of light, emergent light, is very small. Let me demonstrate how fast it is. Are you guys ready? Did anybody wake up yet? Okay, thank you. Oh, my slide went ahead. Okay, so there's two couplings in that Lagrangian I put up there. One of them is the speed of light, and one of them is the fine structure constant, alpha E, the coupling. So what about it? Well, let me remind you what it is in our universe. And it's nice because you get to invoke lots of important names in doing that. So Dirac told us there is an elementary charge, E. Coulomb, long before that, told us that two charges interact with an inverse power law, E squared over R. That's the energy of interaction. Planck and Einstein jointly gave us Planck's constant and the speed of light as being important. And if I look at the dimensions of h bar c, I find that they are the same as the dimensions of E squared. That is energy length. So if I divide, I get a pure number. And it is a dimensionless measure of the elementary charge in QED. Okay? It is small in our universe. Okay? 1 over 137, roughly. I don't think anybody really knows why, but there are a lot of consequences. My favorite is that it's why we teach electricity and magnetism as a separate course from other parts of physics, because if we were more strongly coupled, it would be hard to separate. There are small light-matter interactions, there's weak photon-photon scattering, The famous, sort of most famous result here is the calculation that the anomalous magnetic moment G minus 2 is alpha over pi, the leading order in QED. Very nice estimate is that if you want a stable atom, you get an upper bound on how big the atomic number can be, which goes as 1 over the fine structure constant, because as that atomic number, the number of protons, gets larger, the electrons that are whizzing around are going faster and faster, and they hit the speed of light at this. And that's a dimensionless number of atoms, or number of protons. It turns out to be 1 over alpha. So that's roughly why the periodic table ends, stable elements end at around 137. Okay? Good. So how big is it in, I should say, you know, full disclosure, if you guys didn't get it, how big this coupling is in emergent QED and quantum spin ice has absolutely no bearing on any questions that I just raised about the universe. Okay? Right? But it can give you some sort of perspective on how to think about what the coupling means. Right? Okay, so how big is alpha in spin ice? Well, the trick in doing this is that we want to actually measure it in a microscopic model of spin ice. And it's just a parameter in the long wavelength theory. So we have to do microscopics to get there. Okay? And it's a bit tricky. And it wasn't done, even though, I don't know if you noticed, but the papers which sort of confirmed that the ice model was in the deconfined Maxwell phase and actually measured the speed of light all come from 10 to 15 years ago. None of them actually measured this coupling. Okay? And I think there are various reasons for that. But the main one is here. Well, how do you measure it? We could imagine what we want to do is measure the numerator, that is, like how much energy it costs to hold two charges some separation apart, and the denominator, the speed of light, at long wavelengths. We're not interested in the very short distance physics. We want to know what the effective couplings are. And the speed of light you can get from, in say a numerical calculation, the dispersion of the ground state energy with the momentum you force into your system, because that'll be carried by an excess photon. And that actually was done quite a while ago. It's one of the ways that people confirmed that these systems were in a deconfined phase. However, say that I want to compute the energy between two probe charges and I put them in some computational cell. There's my cell. Does anybody notice the problem with those dipole fields? Right? They're not periodic in my cell. I'm going to completely screw things up. There are huge finite size effects if you try to put a probe charge into a computational cell, a pair of charges. This is a bad idea. So don't use them. And you say, well, how do you measure the energy associated with an elementary charge if you don't put any charges in your system? And it turns out the trick is that in the ice manifold, the electric flux through the periodic boundaries is topologically conserved. That's a lot of big words if you don't do topological physics of this type. Let me unpack it for you with a picture. This picture was designed to make you all go blind. While you all check that every node there has 2 arrows in and 2 arrows out. Right? Everybody blind? Okay, so I guarantee to you that indeed I went blind making sure that all the arrows had 2 in, 2 out. Now I'm going to take a spin and flip it. I flipped that one. That created 2 defects. And there they are. And now I'm going to drag one of them around my system. Woo! Through the periodic boundary. Keeps going. Ah, there he goes. And I bring him back where he started and re-annihilate. And what you see is that I've left behind a unit of electric flux passing across the system. And I can measure that. There, I draw these imaginary lines. What are they called in intro E&M? Gaussian surfaces. You draw these surfaces and integrate E dot dA through them. Put a sphere. Okay, whatever. So that's what they are. In the periodic system, I have these non-trivial ones. And I can just count how many spins are pointing left through it or right through it. And that's a number. So, you know, through this vertical one, there are 2 spins pointing to the left and 3 spins pointing to the right. 1, 2, 1, 2, 3. Minus 2 plus 3 is 1. Down here, I have minus 4 plus 4, it's 0. So in this 2D version, I have 2 integer quantum numbers, which are the topological quantum numbers for this electric field configuration. And in a system in which I do not allow charges, there is no local dynamical process that can change these numbers. So that is the sense in which they are topologically conserved. And so I can do computations numerically that exploit that. And in particular, if my system is in a deconfined phase, and I force as a boundary condition that there is 1 unit of flux pointing in some direction through here, then the system will delocalize the electric field in order to minimize its energy, and it will be uniform. And you can use that, then how the energy depends on this flux quantum number, to sort out what is the field energy associated with a unit of electric charge. Yeah?
Is there one parameter in this Hamiltonian or 2? So the original ice Hamiltonian had this J, but then it has a fluctuation parameter also, yes? Mm-hmm. So it's 2. Mm-hmm. Any more?
I can give you more if you want. How many would you like? So
this is not a stupid question, because your simulations are done with that Hamiltonian, not the field theory. And I sort of need to know what Hamiltonian you are using to do the simulations with.
Right. So the answer is that this data is collected in the pure ring exchange model, which has 1 parameter, but once you make it dimensionless, no parameters at all. Okay? That's projected into the ice manifold. However, let me just explain this and I'll come back to your question. Okay? So this is basically saying that I can get the E squared by looking at the dispersion of the energy in some large, there's 96 spins in these ED, set of exact diagonalization numerics as a function of, with appropriate geometric factors, the flux boundary conditions. That's what these plots are. And they look like they spread quite a bit. It's actually a little misleading. There's way more black dots on the center there. You just can't see them. And you get some number, and you get some number from energy by momentum. You have to do a little fitting to interpret everything. And what you find is that alpha is about 1/10. Okay? Divide, you get 1/10. Now, I view that as large in the sense that it's 10 times bigger than alpha in our universe. Of course, it's small in the sense that it's 1/10, and probably you can do reasonable perturbative expansions if you were computing in the field theory. But it's bigger. Now, what about this question of multiple parameters? So I claim that alpha is 1/10 is the natural scale for the deconfined phase in quantum spin ice, period, whatever your parameters are. If I vary microscopic couplings, and I have various other terms I can turn on and vary, I can vary alpha, because it is much like the stiffness in a Luttinger liquid in 1+1 or Kosterlitz-Thales. It's actually a marginal parameter, and the field theory is well defined for any alpha. And so it can vary as I vary microscopics. That's true. The point is that it varies on the scale. I can sort of tune it down to 0 and then it'll confine, or I can tune it up to roughly 0.2. And whatever you do, and there's various things we've tried to do, and also look through sort of the literature on compact U1 lattice theory, you never are able to drive it above around 0.2, 0.22. And there's actually a conjecture, which remains a conjecture, due to Carty, 1980. I mean, how many times have you heard something like, oh, there's a beautiful conjecture due to Carty, 1980? Okay, so anyway, here's one of them, where he conjectured that there's a universal upper bound in the pure compact U1 lattice gauge theory for alpha beyond which necessarily the magnetic monopoles in the theory condense, by an argument which is too complicated for a colloquium. But it remains a conjecture. I will say we've looked through, I mean, it's been tested numerically in a lot of different models. Nobody's ever seen it go above about 0.22, whatever they play with. So now, what I think is the correct way to interpret that is that basically this is the range. If you get lucky and your material is going to realize this phase at 0 temperature, alpha is going to live in here. Okay? And you would guess it's a 10th plus or minus change. You shouldn't guess it's 10 to the negative 4, because that means you're very finely tuned next to a phase boundary. Okay? So, sorry. I hope that answered your question without being too...
No, but I can ask it offline later.
All right, fair enough. Okay, so let's... good. Let's talk about a few things that maybe you could see to probe this emergent QED. So, neutron scattering. So one of the main probes of these kinds of magnetic materials is by inelastic neutron scattering. And why? Because if a neutron comes in, it deposits energy, momentum, and can flip a spin, right? And when it flips a spin, as we saw at the beginning of the talk, that creates a spinon and anti-spinon. And if I'm in this quantum regime, then those should be two independently propagating excitations, right? So the neutron spectrum, we would expect, will probe pair production in this effective theory and should see two particle continua above a gap, which disperse with the total momentum deposited in those spin-on, anti-spin-on pair. That's essentially the mean field prediction of the effective theory. Of course, if you believe what I said about there being interactions, that is, there's a coupling alpha, then there should be something more than that as well. Okay? So there is. Right near the threshold for pair production, the spinons you're creating are slow, if you're just above threshold. And so it's fair to neglect the radiation that you should also create in an interacting theory. And you can treat the problem as essentially a Hamiltonian problem of two particles, which have a Coulomb interaction and some short-range UV physics. And the point is that those final state interactions at long distance matter. The E squared over R part matters. I could explain why there's some universal physics, blah, 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 but really it's not so important. They matter. And they lead to various effects. One way to think about it is sort of by analogy with excitons and semiconductors. If I can get all kinds of effects which come from the fact that the electrons and holes that are created actually attract each other and might be able to form bound states, that's what that peak is, or sort of enhanced beyond that square root turn on here, density of states for the response. This is the sort of non-interacting prediction, and this is what happens if they attract each other. So those are called Rydberg bound states, and the enhancement I just pointed at is known as the Sommerfeld enhancement for ionized states. And actually something that goes beyond semiconductors is that in a semiconductor, if you're looking at excitons, it's really hard to probe finite momentum because photons don't have it. And so here, it's not so hard. And so there are additional interactions at this level of approximation. You can compute something about, and that modifies the total form of the dynamic structure factor. Essentially suppresses the attraction a little bit. Doesn't really matter what this formula is. The thing which is qualitatively clearest, actually maybe I should have just jumped to this, is that there is a threshold beyond which even at a threshold in the momentum deposited, beyond which even barely created spinon and anti-spinons are co-propagating faster than the speed of light in the system, and they start Cherenkov radiating the photons. And this leads the line shapes to become extremely diffusive. So it smears everything out. Okay. So when you put that together, as I said, all these guys walk into a bar, and they draw this picture on a napkin. And what it is that instead of just having sort of this smooth square root turn-on at the bottom of a two-particle continuum, there's a pileup of response near q equals 0, perhaps with bound states as well. Okay? So all of these effects are dependent on this coupling alpha not being 0. So a tenth is good. Okay? Okay. Now, in the last couple minutes, let me tell you about something which I'm kind of, well, it's sort of our most recent attempt to come up with ways to measure something different. There's issues I haven't talked about with how neutrons work in probing these kinds of things. So can we come up with other ways to look for emergent QED type effects? Okay? So here, the question we started thinking about is, you know, I have an emergent QED, and I have an honest-to-God QED, or Maxwell theory. The honest-to-God one has capitalized letters, and the emergent one has lowercase letters, right? They look otherwise the same, right? So I can ask, how do they couple at long wavelengths? And in order to answer that, I need to understand what kinds of vectors E and B are. We know that they are polar and pseudo or axial vectors in our world, also true in the emergent theory. But essentially, because little e corresponded to a spin, it's the one that is the pseudo vector. It's the one that's t odd. Okay? And what that means, this is a table, but what that means is that I can write two terms that couple these at long wavelengths. One of them is a little e dot big B term, and one of them is a little b dot big E term. Okay? Just symmetry allowed couplings. Okay. What does it say? An honest-to-God electric or magnetic field induces an emergent magnetic or electric field. That is really easy to get confused, but there are effects. So, actually, the first one, everybody who does spin-ice, classical, or quantum already knows. It's kind of the obvious one. It's that well, what this says is that an honest magnetic field couples to spin. Okay? Nobody's surprised. And at long wavelengths, it couples to this emergent electric field because that is essentially the coarse-grained spin field. And what it tells as a piece of phenomenon is that if I have a charge, the spinon, remember that meant that there was a divergence in the spin field, which once I coarse grain means that there's a divergence in the magnetization field, which means, and people, this is why part of the literature calls those objects magnetic monopoles, they are magnetization monopoles. Okay? Well established in classical spin ice. The other one is weirder because what it says is that this emergent magnetic monopole binds real electric charge. And so there's, binds in the sense of like divergence of polarization in your material. Okay? So if those things are moving around, then they should contribute to response in conductivity or dielectric, right? Now, unfortunately, the amount of charge they bind is not very big, so we don't actually think that's going to be the easiest thing to measure. A somewhat more interesting prediction of this coupling is that if I apply an electric field out of the plane to this system of spinons, or to this spin-ice system, that induces the internal magnetic field, the emergent magnetic field. And if the carriers, the charges, were moving, they should feel a Lorentz force, and thus move transversely. But there's no Hall effect because there's as many positive as negative spinons. So it's sort of exactly compensated out. However, if you can put a thermal gradient on and an electric field, then that will induce a drift number current. And in steady state, the upshot is that your spinons, your positive ones drift up, your negative ones drift down, but what that actually corresponds to is a magnetization that's perpendicular to those two. So that's a Nernst effect. And it's a peculiar one because it's saying I take a system and I apply a gradient of temperature and a perpendicular electric field and I get a magnetization in the third direction. Okay? So although we expect this to be a small effect because that G, the coupling involved, is small, we're kind of cautiously optimistic that it's not crazy to measure it because it's not obvious where such a signal comes from other sources. Okay. So with that, let me thank my collaborators. I'll just point out Sid was my postdoc, and he's actually the person who kind of got me thinking about this area. He really wanted to work on it some years ago. And our first paper in the area was along with Frank, who Sid went to go work for him after he was working with me. Sal was an undergraduate honors student. He did his senior thesis with me and did the numerics on that fine structure constant part of the talk. And then he went to Cambridge for a year, and now he's a graduate student with Xiaogan. And then Roderick and Claudio, who I've worked with for a long time. So in conclusion, quantum spin ice, compact UON gauge theory. The natural scale for alpha is large in the sense of a tenth and tunable. There are magnetic versions of all these sort of nice effects, Cherenkov radiation, Rydberg state, Sommerfeld enhancement, et cetera. And we believe that the long wavelength couplings between real electromagnetism and this emergent thing can lead to maybe this measurable Nernst effect. So, thank you very much.
Okay, I'll start. What happens if you dirty it up?
It's, well, to what part? I think, so there's work on...
If you really make some of this stuff,
yeah,
it's going to be not imperfect.
Correct.
And so what happens if you introduce imperfections as you would have in a real experiment?
Well, depends what thing. So I think, I don't know the answer for this Nernst effect. I think thermal effects are going to be a bigger problem in real experiments, actually, of which there are many thermal effects. Because in just talking about whether or not you get photons and you can say whether or not neutrons might see them, then if I remove, yeah.
Here's a specific question.
Okay.
Is the photon's a soft mode?
Yeah.
Right? If you put a perturbation in like that, is it protected? Or can it localize? Can you get a localized state out of that photon that in QED would be impossible because the gauge principle prevents it. But here, there is no such principle that I can see. It's just some defect in the model. I mean, I haven't worked this through, so I don't know. I'm just curious. So can you localize the light?
If you localize the light, you'll localize the phase. I mean, in the sense that probe charges won't separate anymore. So I think you can localize it if it gets to the point where...
That's not what I meant. Okay?
Yeah.
Localizing the light would be, in real life, you take a glass bead and you find a normal mode in it that sticks on the glass bead and won't propagate. And so that's the ideal Maxwell's equation. It'll ring forever, but it's localized. It doesn't propagate. It doesn't have a linear dispersion relation anymore because of the stuff. Now, you've got opportunities for having stuff in there. And
yeah.
I'm just wondering what happens to your soft mode if there's stuff.
Well, I think it depends on how strongly the stuff batters your system. So if there's a little bit of modulation, like a bead's dielectric, I think you could imagine that there are similar effects for the higher frequency part. My guess is that for the lowest frequency part, it'd be very hard to localize at long wavelengths, unless you literally have cut up the spin ice into pieces that don't allow the charges to separate. So, but that's a very strong UV effect. That's not like a little perturbation, right? Now, if I pop a spin out, then you get charged defects. That's a natural defect. You get charge defects, half charge, some state which has some half charge bound to it that can be plus or minus. At least at the leading level, if you had those dilute, I don't expect that they will have much to do with the photons, which can pass right past a frozen charge, because they don't have much internal dynamics. So, it's actually an interesting question, which I've thought about a little bit. I think it's complicated to understand what's like perturbative. You know, if I just take the field theory and wiggle things a little bit, it's pretty stable. But if I start punching the microscopics by defects, then you have to really think more carefully about what does this defect do or that defect do. And yeah, anything.
Vicissitudes of chemistry.
Yeah. So and of course, in terms of real, like what you see kinds of phenomena, it's difficult because, you know, then you have to decide, are thermal effects more or less important than these disorder effects and that kind of thing. So it's the systems which are experimentally best established are the holmium dysprosium titanate, which are classical spin ices. And what classical means there is really that you can understand their dynamics and both their equilibria and their dynamics in terms of a picture of, in appropriate temperature regimes, dilute sort of interacting plasmas of these monopoles along with heat bath dynamics, very incoherent dynamics. And then you can think about what do defects do and so on. The quantum case, the temperature effects, I think, are a bigger problem for the near term than the disorder effects for hoping to see anything coherent, like a Hall effect or Lorentz force or anything like that. So,
one of the most difficult things to compute in field theories with monopoles, even when the coupling is weak, the electric coupling is weak, is what happens when you make a rather high energy collision of, let's say, elementary quantum photons or electric charges. What's the rate for producing monopole, anti-monopole pairs? Even though you have a weak coupling, basically because the monopoles are made of so many perturbative quanta, it's hard to do. Is that something that you could actually think of experimentally measuring in this analog system? Shooting spin-on, anti-spin-on at each other, and seeing how likely it is to make a monopole, anti-monopole pair?
well, that's more like shooting charges at each other and asking if they produce magnetic monopoles than shooting photons. That's fine.
Even that would be hard. That's also hard.
You can imagine it. I wouldn't make any bets about whether you'll get lucky enough to be able to pull it off.
I mean, frankly, it's not a question of the experiment going in textbooks as a theoretical number. It would motivate more theorists to think about this problem.
Yeah. So being able to launch the spin-ons in a controlled way is what you'd like to be able to do to create like a beam or something like that. And there's how controlled you can be, I don't know. So, I mean, part of the reason we turned on a gradient in temperature was because that creates a drift of these objects, but it doesn't make them like collide and do what you're talking about, which is really sort of out of equilibrium. So, yeah, I don't know. And actually, it's an interesting question. Yeah.
Maybe going back to the beginning or like intro, I was curious whether, like you mentioned that there's this huge degeneracy in the spin ice math as well. Was the single adding a ring, like the single perturbation, enough to completely break that degeneracy of ground state, or is there still more symmetry left over?
It is. I mean, it's lifted in the sense of it's lifted completely, but in the sense of something which has a gapless mode. So, you know, there's photon modes going down to 1 over system size or something like that, 1 over linear dimension. But yeah, no, it lifts it. So you do get a unique ground state, and there's nothing symmetry breaking or anything like that.
Okay, if there are other questions, let's thank Kristen. Very valiantly trying to.
So you ran faster than light and went back in time.